All right, we are back, and Myopic Turtle is ready to rock and roll with spin, spin, splitting. The deal is, when you look at your NMR spectra, you find that when you have a methyl group or a CH2 group, most of the time they do not give you one peak. The resonance is actually split into multiple peaks. You often find that the resonance is split into 2 peaks, a doublet, or 3 peaks, a triplet, or 4 peaks, a quartet. There are other splitting patterns too. All right, what's going on here? Why don't you see 1 peak per resonance like we do with carbon-13? Well, the first thing we'll discuss is the answer to that question, why? Why do we get this splitting? Note, this will probably not be that important to you, but it's just good to know where it comes from. Okay, so recall if you have some proton spins or spins in a magnetic field. Remember when you applied the B0 field, as we discussed earlier, that some of the spins line up with the magnetic field, those are the lower energy spins, and some of the spins line up against the magnetic field in the opposite direction, and there's an energy gap value, a delta E here, and recall when we add our radio frequency energy, we get a spin to flip from along with the magnetic field to against the magnetic field. That energy gap is a certain frequency, and that frequency gives us our peaks on the NMR chemical shift frequency scale. Also recall, we're using radio frequency energy, very low energy, and so we know that this energy gap is actually pretty darn small. Because it's so small, we have found that if you had 1 million spins, in general, for every 1 million spins, 500,001 will be in the lower energy state, 499,999 will be in the upper energy state. It's a difference of about 1 in a million or so. Meaning, well, 500,000, that's essentially 500,000. We really got a pretty close to 50-50 mixture. Half of the protons are spin up, half of them are spin down. Okay, so let's look at this molecule here. Let's have an oxygen here. We don't care what's on the other side. An oxygen bonded to a carbon. This has an R group here. We don't care what that is. There's a hydrogen, let's call this HA, bonded to this carbon. And just for argument's sake, since it's next to an oxygen, let's say this hydrogen comes at 4 ppm. That carbon is bonded to the next carbon over that has 2 R groups on it, something other than hydrogen. And it also has HB, a different hydrogen. So we've labeled this hydrogen HA and this one HB, so we can differentiate between the two. HA comes at 4 ppm, HB, let's say, comes at 1 ppm in their chemical shift values. Okay, but here's the deal. When HA is looking around, note, these are spins, they do not have eyes, they do not look. Well, although the word spin does have one eye in it, it's a different eye. But these are spins, are not looking around, it's just, they're really feeling magnetic field. So when HA senses magnetic fields around it, the question is, what does it sense? Well, one thing it senses is our B0, our main magnetic field, the very large magnetic field. That's one thing HA feels. However, recall that HB is a proton that is either spin up or spin down. In fact, 50% of HBs are spin up. And if HA happens to be in a molecule where HB is spin up, then A feels the main magnetic field, plus it feels a tiny little extra magnetic field from HB. So this little extra HB magnetic field adds to the main magnetic field. HA feels a slightly stronger magnetic field due to the fact that HB, its spin, is lined up with the main magnetic field. However, that's only 50% of them. Only 50% of HBs are lined up with the magnetic field. The other 50% are anti-parallel. They are aligned opposite. So if HA happens to be in a molecule where HB is spin down, then HA feels the main magnetic field, but HB is spin down, it's in the opposite direction. It's going to subtract just a little bit of magnetic field from what HA feels. So HA will feel a slightly smaller, a slightly weaker magnetic field. In any given sample in the NMR tube, you've got gazillions of these molecules, right? You've got a whole bunch of them. Half of them have HB spin up, half of them have HB spin down, which means in half of them, HA is feeling a slightly larger magnetic field. In half of them, HA is feeling a slightly smaller magnetic field. Different magnetic field strengths mean different frequencies needed to flip the spin. Now these are very tiny differences, so they are very minor changes to the frequency needed, but what it does is instead of having one signal, HA will be split into two peaks, because 50% of HAs feel a stronger magnetic field and give this signal, and 50% of HAs feel a weaker magnetic field and give that signal. Note, we still have only one HA proton, therefore the combination of these two peaks will integrate to one. Each individual peak in general will integrate to a half. Whenever you're on the instrument and you're integrating peaks, if you see, oh, these are two peaks, it's a doublet, integrate them both together so you get that one. Never integrate a half and a half. Always integrate them together. All resonances, all multiplets, you integrate as one peak, because it is one resonance. These two peaks are due to HA. One HA proton, so you need to integrate them together to get that value of 1. Okay, but what about HB? What does HB see as it's looking around? How does HA affect the magnetic fields of HB? Well, HA affects magnetic fields of HB the exact same way HB did when HB affected HA. When HB looks around, it notes 50% of HA are spin up, 50% of HA are spin down. Therefore, HB is also a doublet. So if you looked at the NMR spectrum of this, what you would find is HA is a doublet centered at 4 ppm, and HB is a doublet centered at 1 ppm. This is our spin-spin splitting. The spin of HB splits HA signal. The spin of HA splits HB signal. It is also known as J coupling. Now, a few things to note. Note number 1, J coupling usually is a constant. So if HA is split by HB and HB is split by HA, these two differences, the width, but the distance between those two peaks, it will be the same for these two peaks in the doublet as these two peaks. This distance is the same as this distance because A split B and B split A. So we call these J coupling constants. They run around 10 hertz, and everyone will say, well, it averages 11 or I like nice round numbers. Coupling constants are roughly 10 hertz. What it means then is for a 500 megahertz instrument, well, that's 500 million hertz, 1 ppm, 1 part per million of 500 million is 500 hertz. So the distance between 1 ppm and 2 ppm on this scale is a distance of 500 hertz. Well, what is 10 hertz compared to 500 hertz? Well, 10 hertz is 0.02 ppm. Well, if instead of coming at 1, this would come at like 1.0 1.01, and this would be down 1.01, which means on a 500 megahertz instrument, these peaks are very, very close together. On some of the spectra that we're going to be examining, you can tell they were run on a 500 megahertz instrument, one of your more common instruments, because you can't even really see the splitting. Someone had to go in and magnify it to show you, oh, guess what? This was a doublet here, because just by looking at it, you couldn't see because those peaks are so close together. Note, our instrument is a 90 megahertz instrument. Doing the same math, that means 1 ppm is 90 hertz. So 10 hertz is roughly 0.1. It's like 0.11 ppm. So yeah, if it's 0.1 ppm, that means on our instrument, these peaks are a little bit further apart. They are much more easily seen, these doublets and these triplets. They are much easier to see on our instrument. Now, that has some bad things too, as people found out in the 1970s pretty quickly when they were dealing with 60 and 70 megahertz instruments and 90 megahertz instruments, that when your peaks are very wide due to the coupling constant, because your magnetic field strength is very low, then they kind of overlap each other, and that makes things nasty. Once we boosted up to 300 and 500 megahertz instruments, you got much less overlapping of your peaks. Even though it was tough to see when you looked at your spectrum, you could easily have the computer blow it up, enlarge it so you can see the splitting, and you didn't have to worry about overlapping nearly as much. All right, so that's nice for our first molecule when we had one hydrogen on one carbon and one hydrogen on the carbon next door. Question though, what about this? It looks like the same molecule. We have an oxygen, a carbon with one hydrogen on it. We'll call that HA again. But now the carbon next door has two hydrogens on it. The question is, what possible combinations of spin does HA see? Well, this spin could be down and that spin could be down, represented here. B1 spin is down, B2 spin is down. Note, this spin could be up and this one would be down. Note, if HA sees, okay, the magnetic field gets a little bit extra added to it by this one being spin up, but then that same amount gets subtracted from it because this one is spin down, a spin up and a spin down cancel each other out. Well, that's if this is spin up and this is spin down. You could have this one spin down, B1 spin down, and B2 spin up. And that still will cancel, they will cancel each other out. And the last thing we could get is both B1 and B2 both spin up, which would then add to the magnetic field. So what does this mean? We have one situation where they're both down, two situations where one is down and one is up, and one situation where they're both up. We will get a 1 to 2 to 1 triplet due to this spin-spin splitting. This spin-spin splitting, note, this triplet is what proton A will be split into. A is split into a 1 to 2 to 1 triplet because there are two proton Bs next door. All right, so here is proton A. Remember, proton A comes at 4 ppm. Proton A is split into 1 to 2 to 1 triplet because there are two HBs next door. But note, all three peaks together of this triplet integrate to 1. So when if you see a triplet, integrate all three of them together to integrate to 1. Very important. This is HA. It integrates to 1 because there's one HA proton. It is a triplet because there are two HB protons next door. All right, now what does HB see? Well, HB over here, there are two of them. Well, they're identical. They have the same chemical shift. This one sees one HA that's either spin up or spin down. This one sees the same HA that's also either spin up or spin down. Therefore, they see the same thing. These two together will give you a doublet. It's a doublet because there's only one proton next door. It comes, let's look at this again. The chemical shift is 1 because that's the chemical shift of these Hb protons. It's a doublet because there's one proton next door on Ha. But since there are two B protons causing the signal, it integrates to 2. Now, everyone's probably a little bit lost right now, but the thing to remember, the thing that makes proton NMR so powerful is this spin-spin splitting tells you the number of hydrogens on carbon next door. The peaks give you information about what is next to them. This peak here is a doublet, which tells me, oh, it's a doublet, there's one hydrogen on the carbon next door. This peak here is a triplet. This resonance is a triplet, which tells me, there are 2 hydrogens on carbon next door. Well, let's crank it up a notch, shall we? What if we had 3 Hb hydrogens? What if we had 3 hydrogens on carbon next door? Let's take a look at that. All right, here's our situation. Oxygen, carbon, 1 Ha proton, but this is a methyl group. This is a carbon with 3 hydrogens next door. The big question, what are all the possible spin values we can get with the 3 hydrogens next door? Note, each individual hydrogen is either spin up or spin down. But this one could be spin down, this one could be spin down, that one could be spin down. All 3 of them could be spin down. This one could be spin down, and this one could be spin down, and this one could be spin up. Or this one could be spin up, this one could be spin down, and this one could be spin down. Or this one could be spin down, this could be spin up, and this could be spin... how many different combinations can we get? Well, we can get down, down, up, down, up, down, down. 3 combinations of 2 downs and 1 up. There's also 3 combinations of 1 down and 2 up. Down, up. So down, up, down, up, down. 3 combinations there. And finally, we could have all 3 of these being spin up. So, what does HA see? Well, here's the deal. On any one individual molecule, any individual HA molecule, any individual one of these molecule, HA sees one of these possibilities and gives a signal for that one possibility. The deal is we've got a whole 1 × 10 to the 22nd of these molecules in your sample. Therefore, while each individual one only gives one of these values, one of these ups or down ups or whatever, when you look at all the molecules together, they add up to this 1 to 3 to 3 to 1 quartet of signal. Note, the 3 HBs cause our 1 to 3 to 3 to 1 quartet, but they cause it for HA's resonance. Recall HA occurred at 4 ppm, so this 1 to 3 to 3 to 1 quartet occurs at 4 ppm. And since there's only one HA proton, it will integrate to 1. It'll be a 1 to 3 to 3 to 1 quartet that all together integrates to 1. What will HB have here? Well, these 3 are identical. There's only 1 proton on carbon next door. Therefore, the 3 of them together will be split into a doublet because there's only 1 proton next door. And it will integrate to 3 because there's 3 HB protons. All right, that's the theory. That's how it comes about, but that is only mildly helpful in letting you figure out how to analyze NMR spectra. What do you really need to know? let's look at the bare basics of what we just need to get into your head. Pascal's triangle. Let's start with Pascal's triangle. If you know Pascal's triangle, and if you don't, you now will. If you start with 1 and you split that down into 1 here and a 1 there, what you're always going to do is split this down into 1, because going down this way there's nothing else, so this is just a 1 here. But if you go down this way, note these two can both come together, so this is 1 plus 1 is 2. And this 1 comes down. So the next line, the 1 comes down. This is 1 plus 2 is 3, 2 plus 1 is 3, the 1 comes down. Next line, the 1 comes down, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and the 1 comes down. Next line, 1 comes down, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So that's how you make Pascal's triangle. And we could just keep going on with it if we wanted to. We don't, but we could. But haven't you seen this somewhere before? Where have you seen 1, 1, 1, 2, 1, 1, 3, 3, 1? Well, heck, here's 1, 3, 3, 1 right just up here. Recall, if you have a 1 to 3 to 3 to 1 quartet, how many hydrogens were next door? 3 hydrogens next door. This is what Pascal's triangle gives us. If your peak, if your resonance is just a single peak, that tells us there are no hydrogens next door. If you have a 1-to-1 doublet, that tells us there's 1 hydrogen next door. If you have a 1 to 2-to-1 triplet, that tells you 2 hydrogens next door. 1 to 3 to 3 to 1 quartet, 3 hydrogens next door. Yeah. Note, there's always one more peak than number of hydrogens next door. For example, let's look at this line here. 1 to 4 to 6 is 4 to 1. That's 1, 2, 3, 4, 5. 5 peaks tells us 4 hydrogens next door. Yeah. 1 to 3 to 3 to 1, 1, 2, 3, 4 peaks told us 3 hydrogens next door. So the good news is you don't really have to try to figure out, okay, what's my ratio of all my peak heights in my multiplet here. You just have to count the peaks. If you say, okay, I'm counting 6 peaks here. Well, if you're counting 6 peaks, you know that there's always one more peak than number of hydrogens next door. If you count 6 peaks, you know there are 5 hydrogens next door. At this point, someone's saying, excuse me, how do you get 5 hydrogens next door to a carbon? Well, what do you think about this? CH5, how does that work for you? Your answer should be, well, of course not, that doesn't work for me at all. But what if you had this? What if you had a carbon with 1 hydrogen on it, bonded to a CH3, also bonded to a CH2? Here we have this carbon. How many hydrogens on carbon next door? Well, here's a carbon next door, 2 hydrogens. Here's a carbon next door, 3 hydrogens, 1, 2, 3, 4, 5. So this carbon, this hydrogen on this carbon sees 5 hydrogens next door. 5 hydrogens next door, it'll be split into 1 to 5 to 10 to 10 to 5 to 1 multiplet. All right. And note, this hydrogen will be split into 1 to 5 to 10 to 10 to 5 to 1 multiplet, but what will it integrate to? Well, we're looking at this hydrogen, this 1 hydrogen, so it'll integrate to 1. It was split into multiplet by these 5 next door, but it's still only 1 hydrogen. So the area under all of these peaks must integrate to 1. The bad news then is if I have the area under all these peaks must integrate to 1, but it's split amongst 6 peaks, how tall are these peaks really going to be? They're going to be short. Let's look at this last one down here. If you were to have 8 hydrogens next door, the tallest peak in this multiplet is going to be roughly 70 times taller than the outer peaks. But altogether, all 9 of these peaks, when you add up the area of all of them underneath, is probably only going to integrate to 1. If there's only one carbon causing the signal, one hydrogen causing the signal. Excuse me. So when you get these crazy multiplets like this, it's often very difficult to tell the exact number of hydrogens next door, because these little peaks at the end might not exactly be visible. All right. A few more issues. What we've gone over today is the nice stuff. In the future, spin splitting is going to get nasty. We've gone over what we call first order splittings, where everything is wonderful, butterflies roam freely, dogs and cats don't chase each other, all that type of things. In reality, it's going to get kind of nasty with our spin splitting. The other thing to note is that rarely, extremely rarely, do you ever get spin splitting through heteroatoms, which means if you have an alcohol, you have an OH, that hydrogen shows up in the proton NMR spectra. It's a hydrogen, it will show up, but you won't get any splitting on carbons next door to that oxygen. All right, so what does this mean? Let's end here today on the next page by just looking at a quick example. Let's take a really basic molecule here, small molecule, ethanol, CH3CH2OH. The question is, what would the NMR spectrum of ethanol look like? The proton NMR spectrum. Note, we need to consider all 3 aspects: chemical shift, spin splitting, and integration. Well, we've got to draw the peak somewhere, so let's say the first thing to look at is the chemical shift. All right, well, what do we know? What do we know? Ooh, check this out. This carbon is next to an oxygen. So these 2 hydrogens are on a carbon bonded to oxygen. What's the chemical shift value for hydrogens bonded to carbon next to oxygen? That's right, that's about 4 ppm. So around 4 ppm, we should expect that CH2 to be somewhere around 4 ppm. All right, what about this methyl group? Well, that's kind of saturated alkane range, right? It's just a CH3 bonded to just a CH2, nothing special there. So that comes down around 1 ppm. Note, this oxygen pulls these hydrogens downfield. If everything was a saturated alkane, it would come around 1 ppm. These come around 4 ppm. These 2 protons come around 4 ppm because that oxygen has pulled them downfield by about 3 ppm. That effect is going to be felt a little bit by these 3 hydrogens here. So instead of coming at 1 ppm, you'd expect them a little bit downfield from 1 ppm. This carbon is not directly bonded to that oxygen, so you won't expect much of a shift downfield, but would expect it a little bit. So let's just put these about right here. Let's put the CH3 right about here on our chemical shift, say about 1.4 ppm or so. All right, so those are our chemical shift values. The CH3, the methyl groups, comes, let's say 1.4 ppm, and the CH2, let's just put it at 4 ppm. What will they integrate to? Well, this CH3 has 3 protons. It'll integrate to 3. I'm just going to put a box around it so I know that's my integral value. The CH2 is going to integrate, well, there's 2 hydrogens, it'll integrate to 2. Put a box around there because I know that will integrate to 2. Last thing, spin splitting. All right, so let's look at the CH2 here. how many hydrogens next door in terms of spin-spin splitting. Note, this hydrogen is bonded to this oxygen, a heteroatom. These two hydrogens cannot see this hydrogen. You cannot see spin-spin splitting through heteroatoms like oxygen or nitrogen, so these two cannot see this one. But what can they see? These two can see these three. So if there's three hydrogens next door, what type of pattern are we going to get if there's three hydrogens next door? That's correct. A 1 to 3 to 3 to 1 quartet. Make it a little bit bigger. 1 to 3 to 3 to 1 quartet. Because there are three hydrogens next door. Note, it integrates to 2 because it's a CH2. It's the quartet because there's a CH3 next to it. Now let's look at the CH3. How many hydrogens next door? 2 hydrogens next door. Well, Pascal's triangle tells us 2 hydrogens next door is going to give us a 1 to 2 to 1 triplet. All right. One thing left. Where is this hydrogen, this OH hydrogen? Well, a few things. One, what about the chemical shift of hydrogens on oxygen or nitrogen? That's right, it can be anywhere. It can be anywhere in here. So let's just give it a value. Let's get it away from everything. Let's say that comes at about 2 ppm. All right, sounds good, 2 ppm. Could be anywhere. What will it integrate to? Well, there's only one hydrogen, so it'll integrate to 1. What about its spin-spin splitting? Oh, that's right, it's on oxygen. There is no spin-spin splitting. But we also know that because it's on a heteroatom, it's going to be a broad peak. So around 2 ppm or so, we can kind of expect a broad hump that integrates to 1. Note, since we're looking at area under the peak, the sharper the peaks are, the less width you have in your individual peak, means the smaller the area is, which means the peak has to be tall. These are sharp peaks, so they have to be fairly tall to get an area of 3 under these when you combine them together. If it's a broad peak, well, that's a lot of area. Look at we can see there. So this OH peak is not only going to be broad, but it's going to be really short because we've got a whole lot of area with under broad peaks. All right, so when looking at NMR spectra, proton NMR spectra, there are 2 things we tend to do. What we've done so far is, with this last example here, is here's our molecule. What do you expect the proton NMR to look like? When you get into organic 2, that's a question you're going to have. Before you do a lab, you're going to try to make your product. You should know what the product is that you're going to make. You should be able to predict a fairly reasonable NMR spectrum. What do you think the proton NMR spectrum should look like? You should have a fairly good idea of that before you run it to see if you actually made your stuff. The other thing NMR is used for quite a bit, proton NMR, is, okay, here's something, I'm not sure what it is, just looking at the spectrum, can I solve it? Can I look at the NMR spectrum, do a little logical thinking, and figure out what my molecule is? I would say if you're an organic chemist doing research, my guess is that most of the time you're going to be making a product and you have a good idea of what you're trying to make, and so you're going to be doing the first thing. Well, this is a molecule that I think I'm making. Let me make sure that's what it is. So the proton NMR should look like this. Does it look like this? Yes, I made it. Oh no, it does not look like this. Then you have to do the second part. Well, my proton NMR does not look like what I thought it was, so now I have to use it and solve the NMR spectrum to determine what I've made. And that's what we're going to do next. We're going to do a bunch of solving spectra in the next video to get you used to saying, hey, here's my spectrum, what is my molecule?